Hi all, today we would be implementing 128 tap FIR filter on Neos 2 processor um, using the C code as well as hardware implementation. So it is said that a dedicated circuitry for hardware would improve its performance. So we are going to test and see by how many times the improvement in performance can be achieved. So let's go to QSys to see the Neos 2 processor which we have built. So these are the components which have been added to the system. This is the Neos 2 economy processor, the clock input, the JTAG UART. This is for the connection to the host computer so that we can communicate with the processor. This is the on-chip memory, and then this is our module. So this FIR module has been directly picked up from mini project 2, and a wrapper code has been built so that the Neos 2 microprocessor system can communicate with the filter. It's the performance counter so that we can count the number of cycles. Pure software based implementation versus the dedicated hardware based implementation. So after adding all the components, you make sure that all the connections are made properly. You make sure that there's clock sync and reset sync added to the FIR interface, and Neos 2 communicates with the FIR through the Avalon bus. And so what I've done in my case is I've used the JTAG UART reset as the reset to all my components. So this JTAG UART reset goes into my global clocking reset, and then the clock reset output goes to all other modules to reset all other systems. So going to the wrapper code, this is the wrapper code. The wrapper code has a clock, clear, chip select, address, write data, read data as inputs. So this chip select will be selected whenever you ask it, whenever you put the address of this particular FIR module onto the system. So, and the module being, so the FIR has address from hex 9090 to 9097. So whenever you put any of these addresses, the chip select there would get activated and this module will get selected. And these addresses are put in through the C code using the input output read and input output write functions. So this is your FIR main, which is the main module which has been developed for mini project 2, and the relevant data is the relevant port connections are made here. So going to the FIR main module, so here it implements the mult and add from the inbuilt LPM mult and LPM add functions. So it implements saturation logic here, overflow logic here, and this is the output. So the required modules mult and add are also added to the system, and all these have been borrowed directly from previous mini project. So once this is done, all you have to do is synthesize it. So just make sure that base addresses are assigned and then the clock settings are made, and then start generating the system. This will take a while. So meanwhile we can just go about the C code which has been developed for this. So hello world small template has been used because because this would take less memory for all its instruction to be mapped into assembly and stored on chip. So otherwise, if custom template is used, it's throwing a memory insufficient error. So this C code has been developed by me. So it has multiple memory accesses. It's been developed in such a way that it has multiple memory accesses. So everywhere it has for loop within for loop. So it has like 128 into 128 memory accesses, which in a very bad way deteriorates the performance. So this is the performance counter being called. So performance counter gets called at the beginning of the code and ends at and is placed the ending part is placed after the main code. So in this way you would get the number of cycles the main code takes to get executed on the processor. So this is a pure software implementation again. So this is the hardware implementation where I've taken one set of data and look at the coefficients. So for loop has been written so that always the first write to my FIR module is taken as data and the second write is taken as coefficient, and it is done 128 times. So here also you can this is the actual code actually. So same thing, it's reading thrice just to make sure that the read write cycle, the reading is done properly. And this is the performance counter beginning and then ending. So when this is run on EOS2, it would give us the number of cycles which it is taken. Still generating. So the design has been generated, so it's been synthesized completely. So all you have to do now is compile the generated system along with all the codes which we have, and then place it on the FPGA board. Let's do that now. So this is done just to cross check it, just to make sure that everything is done well. So this is the top module which has been declared so as to provide the external clock input. So to my Neo system, only clock comes externally from an external port. Rest all are there on the FPGA's chip. Okay, since everything is done, now we are just good to go. Make sure that there is USB blaster 0 here, so that it indicates that it's been connected properly. So here it shows that it's 100% successful. That means the system has been mapped onto FPGA successfully. So now we'd have to run the code, the code to communicate with the hardware accelerator. Yes, so this is the one. So we can just so this is the number of cycles which is taken. So make sure that you use either Windows 7 or any other OS which is prior to Windows 7, not Windows 8 or 8.1, because I had some problems with interfacing. Since this is done, so I'll be running the same the complete software implementation on the same Neo2 system itself. So for that, probably I'd have to reset the system and then again try. So let's place system again onto FPGA. Run the C code. So these are the values at all instances, that is multiplying first data with the last coefficient and so on till all the 127 data get over, and finally this is the result, that is the MAC output, and it took nearly these many clock cycles to finish it. And that is so because the C core has been designed on my own, and it has been designed in such a way that it has multiple memory accesses. So here we can see the deteriorating effect of having multiple many memory accesses. This would deteriorate the performance very badly. So this is your software implementation. So you can finally see that the ratio is which is approximately 1000. That's a great amount. That's it. Thank you for listening.